Hello. Now we will understand about the dielectric constant. So we all know that there are some material which we call as dielectric material, which we call as polarizing material. So they are insulators. By default, they're insulators, but these materials are made up of molecules which are having non-zero dipole moment. Okay. So when we talk about these kind of materials, so these molecules inside the material, they are having non-zero dipole moment. The P for them is not zero. So each and every molecule will have its own electric field. So at any reason, at any point, if you want to calculate the electric field, whether this point is inside or this point is outside, if you want to calculate the electric field because of all these molecules, it will be the net summation of each and every electric field created by each and every molecule. So the E net, whether inside or outside, when you will calculate, that will be the net summation of all the electric fields, vector summation of all the electric fields created by each and every molecule, which is polar in this case. Okay. So when this kind of system is placed, in a surrounding where there is no electric field, external electric field is not there. So there is no electric field. Whatever electric field you will see, it will be because of these molecules. Okay, so single molecule will generate the non-zero electric field. But when we want to calculate the net field, it will be due to all the molecules. So at that time, it will be very important about the orientation. It will be important. We have to see about the orientation of each and every molecule. So when we go for randomly selecting the system, all these atoms, all these molecules here, they will be randomly organized, or I should say randomly disorganized basically. So they are randomly organized in the system. In that case, we can safely assume, since they are randomly organized in the system and there are almost infinite molecules are there, we can safely assume the E net due to this system at any point, whether the inside point we are talking about or the outside point we are talking about, E net will be 0. Okay. So this is our system. So basically this polarizing system, the polar system or dielectric system material here, it will not generate the electric field when we want to calculate it. Though each and every molecule generates the electric field, but the net comes out to be 0 because of the random structure. Now, in this case, if somehow we can rearrange these molecules, we know that, if somehow we can rearrange these molecules, in that case we can generate the non-zero electric field due to all of this system. So if we want to rearrange them, it's next to impossible to move the molecules because these molecules are part of the system. But we can tilt them. And to tilt them, we know the torque equation. If you remember, electrostatic, we studied this. The torque acting onto each and every dipole, because they all are dipoles. Torque acting on each and every dipole is equals to P cross E, where P is the dipole moment, which is non-zero in this case for each and every molecule, and E is the external electric field. So if I place this system in an external electric field, so if I generate the external electric field and if I place this system there, then that external electric field will apply the torque on each and every molecule, and because of that torque, these molecules will start rearranging themselves. And the rearrangement that will take place inside the system, that will make the net effect look like this. So each and every dipole will become parallel to the electric field like this. So this is the direction of external electric field. I am taking that external electric field as E naught, and that external electric field will make the system tilt, the molecules of the system tilt themselves. In reality, actually they don't become parallel. Net effect of them becomes parallel. So it will happen like there will be some delta theta here, some delta theta 2 will be here, some delta theta 3 will be here. So each and every molecule will tilt a little bit. And that tilting, a little bit tilting, will create, it will not change the magnetic or electric field created by the dipole. It will not change the magnitude of electric field of this dipole, but it will change the net electric field caused by the whole system. So they will become parallel, and the electric field due to these molecules will become anti-parallel. I call that EP, E-polarizing. So if external electric field is towards right, the field caused by all these molecules will be anti-parallel at each and every point inside the molecule. Okay, so it will become anti-parallel. So this is the thing, the moment you generate the external electric field, you will create or you will induce the electric field due to this system. And the moment you will switch off this electric field, this polarizing electric field will also become zero, because again, the moment you switch off this electric field, the cause behind the tilting is this electric field. If you switch off this electric field, again, these molecules will again rearrange themselves in a randomly disorganized manner after some time, obviously. And again, the electric field caused by these molecules will become zero. Okay, so now you can see there is this external electric field, and if the system would have been the insulator, inside point, at each and every inside point, the net field would have been remain same as the external electric field. But since this system is a dielectric system, then due to the external electric field, this system is generating its own electric field, and that is anti-parallel to the external one. So for inside points, if you want to calculate the net field, if you want to calculate for inside points, that will be E naught minus of EP. I should say E plus actually. But since we are taking the vector summation here, and we already know the direction of EP will be opposite to the E naught. We know that. So magnitude wise, E net will be equals to E naught minus of EP. Now you see, the E naught, the external electric field we are generating. So we know the magnitude of that. And the polarizing field which is being generated here will depend upon the system. It will depend upon the properties of the system, what kind of structure is there, what kind of material you are using, because it's not like there is only single dielectric. There are multiple types of dielectrics are there. So each and every dielectric will generate its own polarizing field. The magnitude of that polarizing field will depend upon the dimension or shape of the material, as well as the material properties, inside properties, internal properties of the material. Okay, so this E net will depend upon the external field as well as the property of the system. Now the thing is, when we calculate the E net, this E net comes out to be less than the E naught. It's always less than the E naught. It's not zero. In case of dielectric, it becomes E net becomes zero. If in this case dielectric, if we replace the dielectric by a conductor, we all know that polarizing field in case of conductor is exactly equals to E naught, external field. E net becomes zero. But this is not a conductor. This is a dielectric material, which is an insulator, special type of insulator. So what we do here, this E net value depends upon the system. So since different system will give you the different value of E naught, that there have to be some property of the system which will